Video lesson. This lesson is found in section 1.2 and the first part of 1.3 in your textbook. And today we're going to learn about segment addition and segment bisectors. So your learning objectives for today are you can use the segment addition postulate and you can identify and use the segment bisector. So let's get started. Let's remember what we learned last time. So last time we learned that a line segment is part of a line. It has two endpoints. In this case, we have segment AB. It's named by its endpoints. So the notation is AB with a line above it. The line has no arrows, okay, because it's not a line, it's not a ray, it is a segment. Okay, so that is read. This statement right here is read segment AB. Okay, so if we want to know the length of this segment, we simply calculate the distance from point A to point B. Okay, so point A is right here and point B is right here. And if you imagine that these are on the coordinate plane or on the Cartesian plane, remember last year in Algebra 1, you guys learned about the Cartesian plane and you guys did calculations in the two-dimensional Cartesian plane. Well, this is just a one-dimensional line segment. Okay, so there's going to be some coordinates. There's going to be an x1 and an x2. These are going to be numbers. Okay, so for example, if B was sitting at 5 and A was sitting at 2, how long would this be? 5 minus 2, which is 3. So the formula is AB is equal to the absolute value of x2 minus x1. Okay, and this AB, notice that there's no line above it. Okay, so that's a distinction you have to notice. So the notation AB is talking about the length of the segment AB. Okay, so this is not called segment AB. This is called the length of AB. Okay, or you can say the distance from point A to point B. So how is this notation, okay, different from this notation? What's the difference? Well, obviously, this segment AB has a line above it, and AB with no line above it is talking about something else. So what's the difference? Okay, AB with no line above it is the length of the segment, which is a quantity, a value, a number. Okay, remember that this is a number. Okay, whereas if you have this notation, segment AB, that is talking about the line segment AB, which is a shape, not a number. Okay, so AB is a number and segment AB is a shape. So AB, the number, is saying, well, how long is it? How long is this? Okay, what is that value? Segment AB is saying, look at this shape. Okay, the actual segment itself. Okay, so they're very different. So it's very important that when you're writing equations about numbers and calculating numbers that you use this notation for numbers. Okay, and if you're writing statements about shapes, you use this notation. It's very important. Okay, so that brings us to our first postulate, postulate 1.2, which is called the segment addition postulate. And a postulate or an axiom is something that we don't prove. It's something that we accept to be true and we use it. Okay, a theorem, on the other hand, is something that we actually can prove. And we actually will go through some proofs for the theorems that we learn in this course. Okay, but this is a postulate. So this is called the segment addition postulate. The segment addition postulate simply tells us, okay, so if you have this diagram like this, you have a line, and then that line is divided into a segment AB, or excuse me, segment AC, and then segment AC has point B in between. Remember what between means from our last lesson. Okay, point B is between A and C. So we can see that this length, this number, this length AC, okay, is comprised of this length AB and this length BC. So this postulate simply tells us that if B is between A and C, then AB plus BC equals AC. Notice that there are no lines above these, okay? Because if you put lines above these, that would be an incorrect statement. Technically, you cannot add segments. We're not adding the segments. That's just the name of the postulate. We're adding the lengths of segments. So AB plus BC equals AC. Okay, if you put a line above this, that would be wrong, and you would get the answer wrong. You would not get credit for that. Okay, all right. So also, if AB plus BC equals AC, then B is between A and C. All right, so I think this is pretty intuitive. Okay, this number is made up of this number plus this number. Okay, so let's go ahead and put that into practice. Okay, in example 1, it says find DF with nothing above it. Okay, so this is a number. It's asking us to find or calculate this number. Okay, so D is here and F is here. So we want to know how long is segment DF. Okay, and what is that value? Okay, so we're given that DE is equal to 23, and we're given that EF is equal to 35. So this 23 represents, you can see it's right kind of in the middle of this segment. So this 23 represents the length of this segment from D to E. 35 also, likewise, 35 represents the length of EF. Okay, so how are you going to find DF? Well, pretty easy. You just add the two. So here's what our postulate tells us. So I think your Algebra 1 teachers probably taught you this, but anytime you're using a formula, okay, anytime you're solving this type of problem, you want to write the generalized form of if there's a formula, you're using a formula, but in this case, you're setting up an equation, right? So set up the generalized form of the equation. So dF is equal to dE plus EF. That comes directly from the postulate that we just learned. Now you go ahead and substitute in those values, okay? So dF equals 23 plus 35. And then finally just add those together, and dF equals 58. Now, here's something very important about geometry. Okay, in geometry, most of our problems are applied. Okay, this is more of an applied math than, say, Algebra 1. Okay, so in this case, 58 represents something. Okay, it's not just some numerical value. It's a numerical value that represents the length of dF. Okay, dF, the length of that. So in geometry, it's very important that we distinguish the lengths of objects by using units of measurement. Okay, so this answer is not complete. Okay, you would have to write the word units after it. Okay, and it's understood that you could abbreviate the word units with just a lowercase u right next to the 58. And I'll understand, your teachers will understand that that means units. Okay, now, if these numbers had units to them, for example, if they were inches, feet, miles, kilometers, meters, whatever, okay, then obviously instead of units, you would write whatever units are given in the problem. But here, because 23 and 35, we don't know what the units are, we just use this generic word units, okay? And be very careful, because technically your answer is incorrect. If you just put dF equals 58, that is incorrect. That's an incomplete answer. You would have to write dF equals 58 units, okay? Now, sometimes in the middle of a problem, we're going to drop the units, but make sure that your final answer has the appropriate units added to it for full credit. Okay, next example. In this example, we're asked to find GH, okay? And what are we given? We're given, first of all, let's look at the diagram. Let's visually kind of pull this apart, okay? So we have a line segment FH, and it is comprised of two smaller segments, segment FG and segment GH. Okay, so we know that the length FH is equal to the length FG plus GH. Okay, what did they give us? Well, they gave us 21, and we know that that corresponds to this length here, FG, and then they gave us 36 with this mark. Okay, This mark here means 36 is equal to, okay, the length that goes from F all the way to H. Okay, so what are we going to do? First, set up this general equation. We know that FH is equal to FG, this smaller piece plus this smaller piece. Okay, so FH equals FG plus GH. Okay, now we can just rearrange because these are all, understand that these are all numbers. Okay, FH represents a number, FG represents a number, GH represents a number. So you learned way back probably several years ago in one of your foundational math classes that there's all sorts of nice things that we can do to rearrange these numbers, right? Like the commutative property, and you learned many other properties, right? Some properties of equality and properties of addition and other properties. Okay, so we're going to go ahead and just rearrange this equation, okay, to get GH by itself on the left-hand side of the equation, because GH is what we're solving for. Okay, so GH is equal to, so GH, this piece is equal to this entire length FH minus this part, FG. Okay. All right, so now I'm just going to go ahead and substitute in my values. So I know that GH is equal to 36 minus 21. And so that leaves us with 15. GH equals 15. So am I done? Go back and look at the question. The question says find GH, but is there something missing with this answer? Yeah, you got it. I have to write units. Very good. Okay, so let's learn something new. Let's learn about segment bisectors, okay? Before we can learn about what a segment bisector is, we have to learn some new terminology. So the midpoint of a segment is the point that divides the segment into two congruent segments. So here's the midpoint, okay, M. Okay, so first of all, we start with this yellow segment, segment AB, and then we go ahead and add this point that is right in the middle. Okay, and we label that, let's just call it point M. Okay, it corresponds with midpoint. Okay, and there is our midpoint. Okay, now what are these marks? These two red marks are congruence marks. Okay, they are how you show on a diagram that the length of this piece, okay, is the same as the length of this piece, or one segment, okay, would map right onto another segment. And what I mean by that is if you took this segment, segment AM, and you chopped it off and you moved it over on top of, or you slid it, you translated it, or you slid it to the right, it would fit exactly on top of this other shape, segment MB. Okay, so, and we'll talk more about congruence in a little bit. Okay, but congruence in geometry means that one shape can map exactly on top of or onto another shape, okay, by a series of rigid motions. And don't worry about that. We'll talk more about that later. Okay, but this is the mark to show that two segments are congruent. They're the same size. Okay, so our notation is, okay, segment AM, that's this segment, is congruent to segment MB. This is the sign for congruence. It's like an equal sign with a little tilde or a little squiggly above it, okay? This sign means congruent, okay? We also know that the length from A to M, is equal to the length from M to B. Now, why did we use an equal sign here and a congruent sign there? What do you guys think? Shapes are congruent. Okay, shapes are congruent. We don't ever say that shapes are equal to each other. Okay, when two shapes are the exact same size, in other words, when they would map onto each other without changing them, okay, but by a series of rigid motions, if you could map one shape on top of the other shape onto the other shape, they're the exact same size, then we say that shapes are congruent. Okay, this is the symbol that we use for shapes. but values or quantities or numbers are not congruent. Numbers are equal. Okay, so this yellow statement AM equals MB, this is saying that a number is equal to a number. This red statement here is saying that a shape is congruent to a shape. This is very, very important. This is a very important distinction that you will use for all of geometry. So please make sure that you are very careful with this distinction. Okay, so now let's move to what a segment bisector is. A segment bisector is a point, ray, line segment, or plane that intersects the segment at its midpoint. So bisect basically just means to cut in half. Bi means two, like a bicycle, two wheels. Okay, bisect means you intersect it and you cut something into two. Okay, and in this case, if you're cutting a segment if you're bisecting a segment, you're cutting it into exactly congruent pieces. Okay. So for example, this green line DC, intersects segment AB at its midpoint M. Okay, so we say that line DC is a segment bisector of segment AB. Okay, you could also just say that line DC bisects segment AB. Okay, so when we have this line DC that is bisecting segment AB, okay, what do you think happens with segment AM and segment MB? What do we know about those two segments? Well, we're going to know that AM, the length from A to M, is equal to the length from M to B. And also we know that segment AM is congruent to segment MB. Okay, again, be very careful about the equal sign and the congruent sign. Numbers are equal. Shapes are congruent. And I put the and in the wrong place. That should be up there. Sorry. Okay, and then we can add these little congruence marks to show that segment AM is congruent to segment MB. Okay, let's move on. So here's an example. So we're given this diagram, and we are told that point M, this point right here, point M is the midpoint of segment VW. So here's segment VW. We're told that M is the midpoint. Okay, and this sentence is a little bit redundant. Okay, the reason why it's redundant is because we didn't have to be told this, because this diagram already communicates that. What marks on the diagram already indicate that M must be the midpoint of segment VW? Yeah, these little red marks, right? These little red marks are congruence marks for segments. So because those red congruence marks are already in the diagram, okay, that already communicates to us that these two pieces are congruent, which means that M must be the midpoint. Okay. But anyways, it's nice to have this information. So we're asked to find the length of segment VM. So how long is this entire segment? What do you think you're going to do? Well, we're going to set up the equation, right? And our equation is simply that the length from V to M is equal to the length from M to W. So VM equals MW. How do we know that? Because M is the midpoint, okay? And then we just substitute in the values. Okay, VM, the value for that is 4x minus 1. And then MW, the value for that is just 3x plus 3. And now it's just a straight algebraic problem, right? We want to just isolate the x on one side of the equation. So what are we going to do? We're going to subtract 3x from both sides of the equation. That'll leave us with just 1x over here. Then at the same time, we're going to add 1 to both sides. So that is going to give us 4 on this side of the equation. Okay, so we know that x equals 4. Great. Are we done with the problem? No. Go back and look what you were asked to answer. The question asked us to find the length of segment VM. Did we do that? No. We found x. So what do we need to do? We need to substitute x into, okay, our expression 4x minus 1. Okay, so we know that Vm is equal to 4x minus 1, so let's substitute in the x into that expression for x. So Vm is equal to 4 times 4 minus 1. So Vm is equal to 4 times 4 is 16, minus 1 is 15. Now, are we done? No. What do we need to add to this answer for it to be correct? Because Vm is the length of a segment. So lengths of segments must have units of measurement. Okay. Vm equals 15 units. Now, when we solve for x over here, how come we didn't have to write units there? That is because x by itself is not the length of a particular segment. X is just part of an expression that represents the length of a segment. Okay. Whereas 15 is the length of a segment. And so that has to have units. Okay, one other thing I want to talk about that you guys are going to be learning throughout the course of geometry are Euclidean constructions or geometric constructions. So Father Euclid and the ancient Greek mathematicians, they discovered how to construct sums, differences, products, and ratios of certain lengths. They didn't learn how to do all sorts of geometric calculations using just a straight edge, not a ruler, a straight edge with no markings on it, and a compass. And I'm talking about a geometric compass, not a north, south, east, west compass, a geometric compass. Okay, so with just a straight edge and a compass, it's going to be amazing the things that you can actually construct. Okay, so in our study of geometry, we're going to learn some of the basic constructions. And yes, constructions are testable material. So it's very important. They will be on the final exam. So it's very important. Some of you are naturally going to be really, really good at these constructions because of your fine motor skills are highly developed. Some of you are going to struggle a little bit, but don't worry. Okay, you'll get the hang of it. Okay, constructions are something that's brand new to you. So it just takes time. It just takes practice. Okay, so we're going to learn a whole bunch of geometric constructions regarding segments, regarding angles. We're going to actually construct some cool polygons. Turns out that there's actually a very limited number of polygons that you can actually construct. And we may do some circle constructions as well. So yeah, some of you are going to love constructions. For some people, it's actually their favorite part of geometry. And then some people, they don't quite love constructions yet. But either way, we're going to do them. And with practice, just have an open mind and a positive attitude. And with practice, I'm sure that we'll all be able to master them. All right, that's all I have for you. For all of our constructions, we're going to use this website. Okay, and you can just Google Math Open Reference, but let me just show you what that website looks like. It's like this. Okay, and it has all the geometric constructions we're going to do. So here's line constructions, here's angle constructions, here's triangle constructions, right triangles, centers and circles, circles, tangents, ellipses, polygons, etc. Okay, and not only are we going to use Math Open Reference, but I'm also going to show you these constructions by hand. Okay. Now it's time for you guys to go have some fun practicing what you learned. There is your homework. Feel free to go ahead and take a picture of that and enjoy. Thanks, guys.